Welcome. This is part two of our walk through Sebastian Raschka's what is it called? Big LLM Architecture Comparison. So, kind of nice to see them side by side and compared a little bit. We can read about each of the individual models, but then I think he does a nice job without going too deep and highlighting some of the differences. And he has those really nice, pretty architecture summary diagrams. So it's like, oh, let's see like exactly, where things differ. So we'll tag team things a bit, but I'll turn things over to you, Warren, to lead our conversation.
Excellent. Let me see if I can get cursor to save this. Yes, you're gonna save it? No, you're just gonna go like that, aren't you? Okay, well, maybe it'll be fine. Maybe we'll be okay. So let me give, okay, yep, you're with
If I had
cursor.
11 inches of dick, ain't no
We-
All
motherfucking
right.
way in the world I'd be a cat burglar.
Oh, hey,
Let
we
me,
can
well,
have,
Lord, let me
we got
have
a
11 inches
visitor.
of dick, dog. I
Excellent.
wouldn't break in nobody out, God. God, let me.
Thank you, Charleston. I appreciate you. That was very valuable. Okay, so we are coming back with Gemma 3N. Let me see if I can get to that section. Okay, cool. So we yeah, do we have any did anybody is there anything we want to recap or that we have further chewed on over the course of the week and that um, is like a thing we want to use as a, or is a thing we want to say before we kind of just like keep reading down or anything like that? Or are we good to just go?
I have nothing top of head, so I would say maybe
Cool.
yeah, just keep
No,
chugging.
perfect. Let's do it. Please, thank you. Okay, and then that is Untitled One. Perfect. Cool. Great. And this maybe real quick. Yep. Okay. I'm not sure if he's going to see it, but we'll see. We'll see how he does. Okay, so Gemma 3N, which was the small device efficiency. We have the PLE layer here, which is the kind of, can we get extra value out of GPU mem? And we have illustration of the savings. So 5.4B for standard Gemma 3 likely refers to the Gemma 3 4B. And then we have PLE data cached to fast storage. So we're only loading 1.91. Okay. And then rotate that out when we need it. Okay. Makes sense to me. Because Google has an interesting way of reporting parameter counts, excluding embedding parameters. Okay, sure. And then Matt Former, we all remember that one, yeah. That
No,
one.
no,
No, we don't. We don't.
no. I don't remember Matt Former.
Okay. Yeah. This is the nested transformer for elastic inference. The one that I remember is can you give me a breakdown of this paper? Um, this is the one that I remember it being kind of or the it was Apple's kind of main, or no, maybe Google's main trick, Sony's main trick, where they would basically like shard out a bunch of smaller like full models, and then distribute that wherever the most like effective place for that to be would be. Um, we've got, yeah, expensive universal transformer, nested submodels, and then Matryoshka feed forward blocks. Nesting lives in feed forward. We train jointly optimize the G nested variant so that all granularities are good. This follows the spirit of Matryoshka representation learning. Okay, sure. Course
Do you know
defense
what?
license.
Does anybody know what that is? Matryoshka.
Yeah, yeah. So what they did is in your MLP you have weight matrices.
Yep.
Okay. And rather than doing something complex or clever, there's no router, there's no nothing. Basically, what they did is they said, in one batch, we'll just roll the dice and we'll use the regular full weights. And
Okay.
then in the next batch, depending on the dice roll, we'll use half of the weights, but literally the first half. So like you just use the Python slice operator. So if the normal weight matrix is like um, 8,000 by 8,000, right? Then they just use weight 0:4,000, and that's the first half.
Okay.
Okay. And then, depending on the roll of the dice, they'll use a quarter. So it'll just be 0:2,000. And depending on the roll of the dice, they'll use an eighth, 0:1. And so these are in separate batches. They never directly talk to each other. But what ended up happening is because if the different subsets of the weight matrix in the MLP were doing different things, then they would cause higher loss on average overall, right?
Okay.
So what ends up happening, even though there's no explicit coordination, is that the most important things that the MLP needs to do are in the first eighth of the weights.
So they're
And then
not,
the next most important things are in the quarter, and then the half, and the least important things are in the back half.
so there, it's not like a random slice. It's just always the first quarter, always the first
Yeah.
whatever.
Yes.
Oh,
Yeah.
interesting.
And so it's very interesting that they figured out that even if we don't explicitly get the different subsets to talk to each other, they implicitly have to, because if
Yeah.
you know what I mean, if
Yeah.
the left quarter wanted to row left and the halfway wanted to row right, then they're going to cause bad loss for each other, right? But if they all agree to row left, so to speak, then even though the quarter can't row as much as the half can row, they're all trying to do generally the same thing.
Right. So it's kind of learning the small model, but then it's also learning the bigger model, but making sure the big model doesn't, it adds to what is in the small model.
So they don't say in the Matryoshka paper, but ultimately they have to do a few more batches to get all these different sizes trained. But it is
Like
very
fine
different
tuning or
from,
something.
no, I'm saying because there's going to be
Oh,
a
oh,
little bit
oh,
of
yeah.
confusion early on, okay?
Yeah.
So you're going to pay a little penalty from that. But if you didn't do this, if you did this the vanilla way, you would do however many batches, right? So you do, your 500 billion tokens on the full size, and then you do another run 500 billion on the half size, and you do another 500 billion on the quarter size, and you would get just as many models, but it would take you more time training. But then the other thing is, if you wanted to swap them out in memory, you'd have to fully swap them out. Whereas here, one of them is a subset of the other, so you actually don't really, you can switch from the full size to the half size just by using only half of the weights.
So here's a
Uh,
question. Um, because I've always wondered why it seems like each model size you start from scratch, right? Um,
yeah.
but if you did something like this, I'm wondering if they talked about this in the paper. If you started with the small size, like just trained the 1/8 size, and then once you got that, and presumably that trains faster because it's smaller, right? At least not too small, but smaller. And then you add the next quarter to
Mm.
it, keep the first set frozen and just train that next set. Um, would it learn it's, in other words, I guess it's kind of instead of intermingling the small and large training, just do the small training first, then add on the next. Does that make sense?
Yeah, I can't remember if they say in the paper, Warren, I don't know if you remember, but I think that this scheme of alternating actually works better.
Better than that.
So the
Okay.
1/8 gets some supervision from the bigger models about the right direction to go, but
Oh,
it
interesting.
will retain the absolutely most important concepts from what the bigger model learned,
Okay, very cool.
right?
And did they
But you
sample what
definitely could do what you're saying, and it would work to some degree. But I think they explicitly said that
they tried
this
that?
ended up
This works
working.
better.
It
That
looks
the quarter-sized model, they then trained a quarter size from scratch with no bigger model at all, and it was worse than the quarter they got as a subset of their Matryoshka.
Interesting. Okay.
I'm pretty
yeah.
sure that was in the paper.
And is it even sampling? Oh, Warren's trying to say something.
Oh yeah, no, I was gonna say it looks basically tracks like did not train the smallest slice first and then add larger slices later. They said they'd train all the nested widths jointly from the beginning.
Right.
And I think they mentioned my intuition on why that might be was layer profiles, right? So I want to keep those as smooth as possible. So I feel like if what I feel like I would want to train the largest slice because I need like a stable surface on which to like start working my way down. You know what I mean?
Okay. That's kind of what Ted was saying is the larger one informs the smaller one.
Yeah.
Was it a weighted sampling or a uniform sampling? Do you recall?
I don't remember the details. Yeah, so if you have the paper up, Warren, in section 4.1, they say results compared to baselines. So they basically compare the performance of the half quarter models to just fully separately individually trained half or separately individually trained quarter. And they got benefit from being part of the bigger thing.
So yeah, we got section 4.1 with the experiment settings, and then we've got uniform by default in 3.2. Randomly samples a map former granularity from a distribution, and then for most experiments, they sample uniformly all p equal. You can tune those sampling probabilities in the appendix is the noted, and then sometimes get slightly stronger submodels. So my guess is they're like, it's good enough. I don't want to mess with the sampler because everybody hates samplers except like me and 4 other people.
Yeah. So in the picture on the screen, the red upside down triangles are separately trained, and the blue is the mat former. And so depending on whether lower is better or higher is better on each of the charts, the blue beats the red.
Gotcha. Okay, so they did try it.
Yep.
Very cool.
Sweet.
Yes. So what this means is that if you have this trained mat former and you have a phone or other device that has very little memory, then you can just use one of the smaller versions. So like I can only fit the quarter size model on my phone, so I'm just going to load that. Okay. But another thing you can do is if you have enough memory and whatnot to load the full size model, you could decide this task I have does not require a lot of accuracy and I want more speed. And so I'm going to use one of those subsets. And you don't have to actually swap the smaller model into memory. It's already sitting there as a subset of the regular model. Okay, so that's the thing they envisioned is that when you're asking it some tough question about, I don't know, stocks or something like that, it uses the full model. And then when you ask it a really easy question like, you know, we were just at a restaurant and they had moink balls, and you just want to know what is a moink ball, and then you could just say, well, for this task I'm going to use the really tiny model, and it's smart enough to know that apparently it is a bacon wrapped meatball.
Well, and I feel like depending on how you split those operations and when they can do the load, because I'm looking at it here, and so we've got text parameters loaded most of the time, but if you're opening a camera app, then you can load up the vision parameters, and then because you know you're going to need those. And as long as you have the per layers, then you should be good to just kind of rotate in and out depending on what you're doing.
Right, and Matryoshka is saying you can use even less than the 1.9. You can use half. Well, it's the MLP only, so the attention parameters will still be there, but vaguely half-ish, quarter-ish parameters.
Yeah, that's between Matryoshka and MOE router stuff. That is a rabbit hole I want to fall down. It sounds fun. I.e., like, okay, we have if there's a way to train a Matryoshka MOE and then have the router be grabbing experts out of the right block of parameters or something. I don't know. There's something there that sounds fun.
What you're talking about, kind of combining them somehow?
Yeah, where it's like, so if what this is doing is it's taking our query, right? And then then it can pick a whole model to load. Well, what if of the available models, what if I just loaded the experts of that model and then also chose whether I needed text, vision, or audio, if those are if those are informing the expert routing at all, then you could just get that little tiny slice of just the right model and activate those instead of anything else.
It seems to me you could have a MOE where you say I'm using 8 out of 250 experts. But then Matryoshka, you could say, what if you only used 4 out of 250? And what if I only used 2 out of 250? Depending on which batch.
Yeah,
Right?
so if you got a phone that's like a big old brick where it's got enough memory, but it just doesn't have the speed, you can just try to hyper optimize down to
Or
one expert.
I think you guys have heard me say I'm not a huge fan of MOE models for smaller devices. So I
Mhm.
wouldn't necessarily lean that direction, but it is an option.
but yeah, but it also affects the inference time, right? So yeah, so you're saying not for small edge devices, but
Mm,
it can be used for inference time.
Yeah, it takes up a lot of memory to do MOE, so it's debatable if it's a great idea for small devices.
The other one I was going to ask is, does it have to be the same? So the model dimension is the same regardless of what size MLP you use, right? So is there anything that says that they have to all be the same MLP size? Could I use small MLPs in the beginning and the end and larger ones in the middle, or mix them or whatever?
So that's the next bullet point, Warren. I think
Oh,
they
did
mentioned the mix and match here in this article.
is it in the Sebastian one or is it in this the
No, I
Matryoshka?
know it's in the paper, but in the Sebastian, do they mention?
Let's see.
No,
Freeway of our
I guess
bonus.
not.
Let's see.
Yeah.
Nothing in the
So,
former. Yeah, according to our assistant,
so
nothing in
okay.
forces the width. Yeah, go for it.
Yeah. So this is the part that I thought was crazy, was
Hmm.
that if you were training it on sometimes full size, sometimes half, some quarter, you could train it where, like, say, the first half of the layers are full size, but the second
Yeah.
uh, half of the layers are half size. They never did that, not even like once, not even in an ablation. But at inference time, they said, but let's just try it anyway, and it worked well, according to them. So, what they ended up recommending is use as similar sized versions as possible. So don't use the full and the quarter, right? Use the full and the half, or the half and the quarter, or the quarter and the eighth, right? Like use consecutive sizes, right?
Oh, when
Um,
you're mixing them?
when you're mixing them, right?
Yeah.
And the other thing they recommend is go big to small, don't go small to big.
Yeah, the thing that sticks out to me here is that the shows that a simple, gradually increasing profile works almost as well as doing as an expensive search over all the combinations, which is
Um,
interesting. And presumably, if gradually
Wait,
increasing
is
is good
this
enough when you're trying to save, then you should be good.
but is that the opposite, Ted? Gradually, would you say gradually increasing profile? Is that what you said? I don't recall.
Mhm.
I don't know what profile means. I recall, I may be misremembering, but I thought they said use the big ones first and then gradually shrink it. Because once you've constrained it and you've lost capacity, then opening it up doesn't necessarily help, right? But if you start in the right direction and then maybe you just get some rounding errors if you use the smaller stuff later or whatever.
Yeah,
Um,
I could also see it the other way that I could think of it as the larger ones kind of adding less noise. So you want to, as you get closer and closer to the output, you want to get less and less noise, or intermixing them too.
yeah,
That
so
would be good too.
that was not their recommendation. I don't know how many different ablations they did. They did tests where
No.
they just randomly picked layers. So like layer one is big, layer two is quarter, layer three is half, and but they said for the amount of savings you get, it doesn't really make sense to mix and match that way,
Gotcha.
right? It kind of makes more sense. So one use case that comes up is, let's say it's 1.9 billion parameters to use the full size model, okay? And you're like, well, shoot, my phone doesn't I can't afford that much memory. Okay. So what you can do is you can use the half size model, which let's just say it's 1 billion instead of 1.9, right? You're like, yeah, my phone only has, 1.5 billion available, so I have to use
Hmm.
the half size model. They're like, aha, but you
Yeah,
could mix and match, and you could
it's
use something that's
fractional.
1.4 by using, you know,
Yeah, yeah, yeah.
half of the big layers and half of the half size layers. And so they're saying that like you could, if you really wanted the max performance for your device on an arbitrary device where they don't know how much, you could pick the exact combination of fulls, halves, quarters that fits on your device.
Uh-huh. Very
And you would
cool.
get theoretically slightly better performance than if you just all went all the way down to all half, all quarter, all eighth.
Gotcha.
I don't know if anybody's really tried it in the real world.
Hey, how
Yeah,
should
there's
we
a hand
find
raised. Question?
Has I was just going to ask, has this been replicated somewhere? Because it seems like a very novel concept. I don't know whether it's like just they doing research or is it like something
Yeah.
they're able to
There,
reproduce? Yeah.
there's so many publications every single day, so I can't say that there hasn't been, but I haven't seen anything else that got buzz that's been widely discussed.
Okay.
We'll see
Um,
if the assistant comes up with anything, I suppose.
that'd be great, Warren. But I will say though that this is not just a research paper. I mean, this is their Gemma model that
right?
Google is saying like this is the model that they are hoping to push onto all Android phones. So they're pretty serious about this model. This is not just a bunch of researchers in some ivory tower saying, "Wouldn't this be cute?"
Okay, yeah, we've got a couple of interesting papers on the side, it looks like, but yeah, I think that makes sense to me where if what they're trying to do is fit it onto their Androids, right? Then they only need something that's like, okay, like combinatorial search like doesn't give us enough performance. This fits pretty well on an Android. We're going to sell these kinds of Androids, so we don't need to like squeeze every bit of performance we can get out of this. So let's just let's take the easy road and ship that. Is my hunch there?
That Flextron looks interesting, applying similar concept to attention.
Interesting.
Yeah,
Yeah.
so the Matt Former paper came earlier. It was October 23, so it's kind of old, but it didn't really get picked up at the time anywhere. And so
Mhm.
it's been out there, uh, but this is the first like really big release model, not research paper, but like release.
Yeah.
And Gemma 3N's only a couple months old, so there's not that much time for other people to
Right.
riff off
Yeah.
of it.
Yeah. Very true.
Before we scroll past it, so what is this per layer embedding then? What's that referring to?
The per labor embedding's interesting. I'm not sure if anybody yet fully understands what the heck it's doing.
Okay.
Um,
Does anybody understand
um,
what it is?
yeah. So when you do embeddings at the very beginning
Yeah.
for a model, okay, um, the way you're taught, I don't know how the code is actually written, okay, but the way you're taught canonically to think about it is if you have a vocabulary of 100,000, there's 100,000 different words in your vocabulary.
Yeah.
Each of those is assigned an integer from 1 to 100,000. Okay. When you get a sentence, uh, you tokenize it and you convert it to a bunch of one hot vectors. And those one hot vectors, have 99,999 zeros and a single one corresponding to whatever word that is.
Hmm.
You take the one hot vector representation as a matrix and you multiply that by the embedding matrix, and then that basically gives you the vectors associated with each word as your input. Okay. But the reality is, it's just a lookup table.
Yeah.
You don't need one hot vectors. You don't need whatever. Okay. And so, because we're doing this on a GPU, that's a relatively reasonable implementation. If you were doing this on a CPU, what you would do instead is you would store these 100,000 vectors as an array, and you would directly use pointer arithmetic to
Yep.
index to the thing
Yep.
that you want. So what they're pointing out is that if they had embeddings that they wanted used later in the model, and you stored them in main memory, then they can be accessed very quickly because you don't need to do a matrix multiply. You just do pointer arithmetic and you read out the thing, and voila, you're done. Okay. So
Okay.
that's trick number one. Use pointer arithmetic, not matrix multiply, to get the embedding. Then what do they do with the embedding? As far as I can tell, it's a gated operation that then just gets added to the residual stream. So, right, the attention layer gets added, the MLP layer gets added, this per layer embedding gets added. Okay. Um, the intuition I have may not be right, but the intuition I have is a little bit like in DeepSeek when they had MOE and they had experts, they had one expert that was always on.
Uh-huh.
So you can think of, you have an MLP that's doing a bunch of different things, and this per layer embedding is like this additional expert that's running on the CPU that's always on. Okay. And so it takes the original token, does this embedding thing, and it adds it to the residual stream. Um, but it is
So it's kind of like
gated.
an MLP that's on the CPU. Is that what you're saying?
I don't take it too literally, but yeah, it's kind of like that. And because it's gated, it means that it can have a little bit of conditional awareness of what the word is for what to do. So it's not just a bias term. It's not like just, oh, add 1, 2, 1, comma 2, comma 3, comma 4, comma negative zero point 0.5 to the
Mm-hmm.
residual stream. There's a little gating thing that happens, is my understanding. So uh, but 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 it's always on at each layer. So it's sort of this kind of like another expert, kind of like another MLP, kind of a thing. What makes it different from the way real MLPs work is that the real MLP at layer 20 takes in the representation coming out of layer 19, and it does its MLP trick. What this does is it always takes the original token and does its embedding thing. So there's no communication needed between layer 19 and the CPU. The CPU can pre-compute all of the layers per layer embeddings. In theory, if it were fast enough, it could compute them all super early in the process. Um, and
But
so
it's a lookup, so it doesn't really have to be fast. It's just a lookup.
yes. And so basically the idea is the CPU can do the lookup and do the slowish, potentially, CPU to GPU copy. Although if it's an integrated GPU, then it might be integrated memory, and it might
Well, and
not
it's
be.
only
But
dimension width. Well, no, I guess it could be more than dimension width because it's actually the MLP hidden state width.
That's an interesting point, though, considering the Apple like unified memory thing and their like MLX kind of architecture that's optimized for it.
yeah.
Interesting.
Um, uh, so it's not clear to me how helpful the PLE is, but I do see that you can fully parallelize this CPU operation with whatever the GPU is doing. That it's small enough in scale that it's reasonable that the CPU can keep up with the GPU.
Yeah, yeah. Well, if it's all keyed off of the token, I thought it was like somehow like the MLP feeding in the residual stream into it, but it's not. It's like the token comes in and all of the layers can get have their PLE. Okay.
Yep.
And
They
then
could all be looked up right away. It's
got
just
it.
a matter of sending it to the GPU at the right time.
Got it. Okay. And did they have a picture, Warren? Did they show what they do with the PLE? Or was that the extent of the picture?
I've not seen Google release anything, but because Gemma is an open weight model, you can just simply run it through uh, anything that will display the computation graph.
Okay.
And so then you can see
But you
mathematically.
your understanding was it's more than just a bias. There's some sort of gating that it affects. They use the PLE for gating as well. Okay.
Yeah.
Okay. Thanks,
Hmm.
Ted. That was very helpful.
Yeah, super. I'm quite interested in the
Yeah,
unified. Yeah.
I will repeat the comment that I made last week. So for some of these models, you have to understand they're not going for the world's greatest state-of-the-art performance. If this is right, your ginormous llama, whatever they call it, behemoth, right? If this is GPT-5, if this is, you know, Claude Opus, you're going for the world-beating performance. In
Mhm.
this case, they're trying to fit it on an Android phone, presumably, but in general, some small device. And so they're making compromises. This is not going to give you the best. PLEs, they're not saying are going to give you the best performance, but it's a compromise. Can I get a little bit better performance than one that doesn't have PLEs? Is it going to be a little bit faster in inference time than if I took all of that and had traditional MLPs all running on the GPU, right? So that's where these different kinds of choices come in. So the Matryoshka and the PLE, all this stuff is not, you're not going to see that in the next version of DeepSeek or Qwen, right? These are all trade-offs for the small, tiny model environment.
Mhm.
Mhm.
Gotcha.
Which, yeah, I mean, yeah, it looks like you can shave like a quarter of this model off if you're in a constrained environment. So that sounds like a win to me. And for this use case, yeah.
Yeah.
Let's see. Okay, we are on to Mistral Small 3.1, released in March, shortly after Gemma 3. Noteworthy for outperforming 27B on several benchmarks except math while being faster. Reasons for the lower inference latency are likely due to their custom tokenizer as well as shrinking the KV cache and layer counts. Otherwise, standard architecture. See, embedding layer, we've got RMS norm and residual stream. Okay, so Gemma's got the the two blocks, and then this has the pre and then the final kind of map model thing. Hidden layer dimension of 32K, and then dimensionality of 21.5 here. 3216 versus 48. Interesting. And then embedding dim is very close. 128, 128. Sample inputs. And then vocab is also identical. And then we don't really have a major, oh, we have a Gilu, a Galu here, and then we have a Silu here, which sounds like a difference to me. Let's see. Interestingly, earlier Mistral models had utilized sliding window attention, but they appear to have abandoned it, and they go GQA instead. Use regular GQA instead of GQA and slide. Maybe there are additional inference compute savings due to being able to use more optimized code because they don't have to run on Androids. Sliding when it reduces memory usage, it doesn't necessarily reduce inference latency, which is what 3.1 was focused on, which tracks to me and makes sense for the use case. Yeah, seems pretty straightforward. Any thoughts, anybody, or we want to keep going?
When they say they reduce the size of the KV cache,
Mhm.
do they mean they reduce the number of like key value um, computations they do somehow, which they don't have to cache anymore?
Shrinking the KV cache and layer count is the thought that the by shrink we mean we're trying to prune values out of the actual keys and values, or like we're trying to like shrink our usage through some kind of like other optimization. Is that kind of what you're getting at, or?
Yeah, yeah, and like there are two ways to reduce KV cache. One is like you actually reduce for example, your sequence length or the number of attention heads, for example. And the other ways are like you quantize the KV cache or you do certain optimizations on the cache, which would reduce its size.
I'm trying to remember the KV cache or using some other.
Yeah, see what the LLM says. I don't
Mhm.
think they did anything other than reduce the number of layers. So they went wider and shorter instead of skinnier and taller, it looks like.
Got it.
Clues, yeah. Let's see. Weight quantization used for the parameters. Public evidence that they have quantized a version Red Hat, but that's not them. Hugging Face discussion. If they use it with FP8, cache data type is configurable in the inference engine settings, but that's also, I think, presumably a Hugging Face decision. Allows for it in lower precision, at least optionally. Not that it's built into the architecture, but
Yeah.
theoretically feasible. Yeah.
So I think it's just fewer layers and using grouped query
Okay.
attention. So presumably cutting keys in half. That's all that they really did. So nothing super special and fancy. Not
Got
like
it.
last week when we talked about the latent attention or anything like that.
Right, right.
Yeah, looks like it's not clear based on this is from non-thinking, so it could be, or obviously there's several hallucinations in there already, but yeah, that checks out to me like standard fare kind of weight quantization, lower precision, D-type tuning kind of thing. Checks out to me. Let's see. Okay, we have Llama 4 up next. Introductory discussion on MOE pays off again. MOE approach otherwise follows a relatively standard architecture. It's very similar to DeepSeek V3. Native multimodal support, similar to models like Gemma and Mistral. We only focus on the text model. So 671, 400B, more smaller experts, fewer bigger. This in basically every time I found this decision, this seems to be like the more performant model when you make this trade-off, or at least in my experience. Vocab is similar. We got Swiglu,
Is it,
2048, 81.
Warren, are you thinking more performant in terms of the accuracy or the inference time?
I am I am measuring by the vibes of the people I know trained making
Okay.
those kinds of decisions, basically.
But by vibes, you mean accuracy.
I would say, yeah, I think accuracy because I don't. They're mostly performance people and not like serving volume people. So my guess is I'm thinking that the like more smaller MOE approach is probably a performance thing, if I had to guess.
Yeah, well, actually, I'd kind of guess that it's like what percentage of the weights or what total weights are active. I don't know how much it affects it, like distributing over a few larger experts or more smaller experts. My intuition would have been that it's like what's the product of the expert size times the number of experts. That's the constant, the apples to apples.
Yeah, actually, I'm because they have DeepSeek V3.1 came out. I want to say like this recently, like a week or something ago. I would be interested to see um, if they have a tech report, what kind of decision they made for 3.1, and if they're kind of keeping that same general thought. Um, let's see, we got anything else
Oh,
interesting? Oh, paying attention here. Yeah.
sorry, Warren, backing up. The previous question, I just was zooming in on the diagram for Mistral Small,
Mhm.
and instead of 2 to 1, they did 5 to 1 grouped query attention.
Mm,
See how it says 40
yeah,
heads, but only
yeah.
8 keys and values?
Yeah.
So that's probably the main thing why he says shrinking the KV cache is because that's pretty aggressive to go from 2 to 1 to 5 to 1.
Oh yeah. Yeah, no, checks out. And yeah, definitely makes sense for on kind of general like on device fits on an Android versus like we just want to serve it small and fast kind of thing. It checks out to me. Let's see. We got the 400B intermediate hidden layers on 8192, and then we have 2048 over in DeepSeek. And then we have router feed forward 1 to 256, 1 to 128 here. Interesting. One shared plus one expert active per token, one shared plus 8 experts active per token. And then 37 per step, 17 per step. The ratio sounds kind of similar to me. 5120, 7168, slight deviation here. Interesting. But kind of ratio wise, still kind of basically the same. Context lengths at 512, and then dense and MOE blocks alternate every second block. Interesting. Hidden size 16384 for dense. First three are dense feed forward with 18 instead of MOE. Interesting.
One comment I'll make is I think DeepSeek has really done the most experimentation on how to get, when you use the many small experts in MOE, how to get those experts onto the same GPU. So it's possible that Meta was kind of looking at whether they use fewer big experts or whether they use more tiny ones, and they may have been a little bit, stuck in terms of how to get the many small things to work right. I don't know, I'm just speculating. But so if you look, what they used is one shared expert and one big expert active during inference. There's no trouble making sure that that is on the right GPUs because the one shared one is always on, and then when you're only using one other expert, it's only ever on one GPU.
Right.
Very
Yeah.
easy to allocate those experts to GPUs for what it's worth.
Which makes a lot of sense to me, i.e., we're not doing sophisticated allocation when we're loading into the GPU with regards to the expert. It's just like, okay, if I can fit half this on one GPU and then I can fit the other half with my expert, then I'm okay. So that would indicate to me that the router is probably going to have to end up doing more work to make sure that it is like it's teaching experts correctly or selecting experts correctly because it has more missed chances, right? Is kind of where my head's going with that.
Yeah, and if you read the DeepSeek papers, they had a loss at first to try to get them on the same GPU, and then they ended up switching to a different strategy. But it seems to like it's non-trivial how to get that to work well.
Yeah, I'm curious. Did anybody end up using Maverick much? Because I remember using it, and my vibe check with it was absolutely horrible. So I don't know if anybody else has experience with using both of these models. But comparatively, yeah, V3 blows Maverick out of the water in my experience.
And then Quen's even better.
Oh yeah. At least from my read, Quen is better if you don't have to heavily quantize it. It starts acting, or in my experience, it starts acting really weird, especially if you go below like FP8. Then it just starts just like doing a lot of nonsense, whereas DeepSeek is very like durable in my experience. You can do whatever you want to that thing and it will still run. Interesting differences worth highlighting: GQA and then multi-head latent, which we discussed. Sure. Large, 68% larger, 37 billion active, and then twice as many active. Okay, so you have a less granular router. It's only picking like one of two. And then you also have like half the parameter count, even though you have a much larger model that's doing more sophisticated routing with more net actives. So it makes a lot of sense to me why DeepSeek would be way ahead of Llama here. Classic MOE, sure. MOE layers in each transformer block except the first three, and then Llama 4 alternates MOE and dense, which is really weird to me. I'm not used to hearing that. Difficult to determine their exact impact on final model performance. Significant relies on popularity. Disagree. This is like pretty clear to me why it's not exactly which architecture decisions are doing what, but the totality of the decisions made between the two, it's very obvious to me which one's going to come out the winner. That's as far as I can see. Yeah, do we want to stop here for anything, or do we want to move straight on to Quen 3?
Quen 3?
Sounds like Quen 3 to me. Yeah, so we've got Quen team crushing it, absolutely. Co-advising LLM efficiency challenge, and they were all Quen 2s. Checks out. Another hit model series. We got seven dense models. So yeah, this structure is definitely I would presume that this passes the TED seal of approval. You're dense up to 32, and then your MOE when you are trying to parallelize, which is kind of, from what I'm seeing, the obvious thing you should do with these. As I can see, we have dense model.
Yeah, the small MOE, right? At 30 billion, active 3 billion or whatever, that's borderline small. You might be able to run that on consumer hardware, depending if how you quantize it, or whatever. So it's kind of interesting, that choice. But clearly the other one, the 235, is meant for server enterprise. It's not meant for
Yeah. I would be
run on
interested to
your own.
see what the Quen team, if they had anything in the model cards about like you should use this here and this here, because I'd be interested to see which one. My guess would be like we really want to try and fit this onto like 16 to 32 gigs if we maybe can, sort of. And then this is like, okay, you're just above consumer and you could just load up this whole thing.
Yeah, so maybe it gives you an inference speed benefit being MOE. I don't know.
Yeah, that checks out to me, I think, actually, just because any parallelization that you have available locally, then you can take advantage of this, whereas you're just kind of like stuck chugging through the whole thing with this. That checks out to me, actually. Let's see. 0.6 model may well be the smallest current gen open weight model out there. Very performant, throughput, low footprint, easy to train locally for educational purposes. We like this. 0.6b has replaced Llama 3 1b. Comparison. Oh, okay, good. Awesome. Okay. Llama 3.2 1b, which is not Llama 4. 131 versus 41 on context length. 0.6b. We have vocab 128 and 151. And let's see. RMS norms are the same, except we have a QK RMS norm. Interesting. We have rope to GQA here, which looks the same. Token embedding layer, Silu, 3072, 8192, wider architecture. Okay, checks out to me. 32 heads versus 16 heads at half the size, sure. And then about half the size on the hidden DIM. About half the size on the embedding DIM. But we're going deeper here because we are doing 28 layers. And then we're doing 16 here with wider dimensions. And then the embedding dimensions. Interesting. Yeah, I'm curious if we were to say, like, when do you want a wider one and when do you want a deeper one when you're at this kind of model range? I'm curious to know the answer to that.
Wouldn't wider be lower latency?
A wider for lower latency. Let's see. I would think, yeah, I would think so. What's sticking out to me here is like the QK on the RMS norm plus you have a deep architecture, whereas you're going straight up with the rope to RMS here with the same number of normalization like steps, if you will. So yeah, it could be a latency related reason. That seems reasonable to me. Let's see. For Llama 3.2 versus Quen 0.6 intuition on Y. One is deep. This one is wide. And what that does for each. Interested in the human 3. Okay, we got a Quen 3 from scratch and pure PyTorch. Let me mute my mic while the sirens go by. In theory, if I can. I can't find the mute button. I guess we'll have to tolerate. Okay. Recently implemented performance numbers in the figure above are based on my implementations. Smaller memory footprints, but also uses smaller hidden layers and fewer attention heads. So just like super tiny all around. More transformer blocks than Llama 3, which leads to slower runtime. So sounds like Llama 3 is
Yeah.
Yep, checks out to me. I don't even know what that is. Iterative, better gradient flow per layer, parallelism, and throughput. Yep, checks out to me. Quen 3 MOEs. Yeah, interesting. So we have 2 flavors of MOE. Why do some come as regular and MOE sparse? Good, excellent. A good section. I like this. MOE variants help reduce inference costs for large base models, and then both dense flexibility depending on goals and restraints. Sure. Dense models are straightforward to fine-tune, deploy, and optimize. And then, yeah, scaling inference here. So that's definitely the observation we've made about these so far. Fixed inference budget. They can achieve higher overall model capacity during training due to being larger without proportionally increasing inference costs. So cost savings during training, interesting consideration. By releasing both types, supports a broader range of use cases. Dense models for robustness, simplicity, and fine-tuning, and MOE models for efficient serving at scale. Yeah, checks out to me.
And just so I can get on my usual soapbox, what
Absolutely.
Sebastian, I'm surprised Sebastian didn't say is what I always say, which is that, yeah, the inference is faster, but you need more total physical GPU memory for these MOE models. And so,
Why is that? Because of the routing?
no, it's because you need all of these experts loaded onto GPUs, regardless of whether they're used or not.
Right.
So
So
when you say I'm using 8 out of 235, you still have all 235 loaded on GPUs.
from a memory
And
perspective, but from a
from,
compute perspective during inference, you don't have to, you're going to have fewer flops.
uh,
So it's not a savings from a memory perspective, but it is a savings from a compute perspective during inference.
it probably is, but it's not absolutely guaranteed if you imagine using one giant honkin' MLP versus 8 smaller ones. The flops could end up being similar-ish.
Well, but if your total size is whatever, what is this, 235, but you're only multiplying the 22, you still have to have 235 in
I'll do
memory,
it myself later.
Yep.
but you're only multiplying the 22. So my assumption would be that the flops for the 22 is less than the flops for the 235.
It's certainly less than if you used all 235 experts, but if you compare it to a dense model that only has, say, one expert and it's just giant, then it's not clear that it's actually fewer flops. It probably is typically,
Yeah.
but you know what I'm saying? Like it's not 100% guaranteed.
I don't know how I mean, I can think of the flops and the memory footprint as pretty straightforward. I don't know how it translates to the quality, the accuracy of the model.
My
But
thought,
I gotta say, I like MOE because the way I look at it is when I go to predict the next token and the next token is
Mhm.
I have to, in a dense model, I have to take into consideration every piece of knowledge I have stored in my entire model. I have to evaluate all of that to figure out the. Um,
Mhm.
whereas in a MOE, it's constrained. It's like it's focusing more on the parts that I need, and I don't need the whole. I don't need to review everything, all my astrophysics and biology and law terms. I only have to evaluate the whatever's in the experts that are selected or routed.
Yeah. I think that's a good intuition, but I think you need to be a little careful because the routers are so dumb that there's only so much smarts you can embed in them as to which expert to use.
But I maybe I have the wrong understanding of it, but what I understood was the routers aren't that smart, but it doesn't matter because whatever they route to, those learn those features. So it's kind of like they don't know what to route to, but it turns out what they route to ends up learning what you need.
Yes, yes, but I'm saying if say start with the very first layer, which is like the easiest because it's right, we're talking about more or less your vanilla input word without
Okay.
any stuff built up, right? But you can imagine that if your router routed the words 1, 2, 3, 4, 5, 6, 7, 8, 9 to the same MOE, that there might be some savings there. But if it routed one doctor, fire truck, rainbow to the same MOE, even though what you're saying about like, yes, they can at least specialize, but remember the vocabulary's 125,000. And so if you have 256 experts, like uh that's a 500 to 1 ratio, right? And if you're using X many experts, then so I'm just saying if you have like 500 completely random words routed to you, I'm not sure how much of a bit savings that is because you have 10 different experts that all have to learn the single digit numbers and what to do with them. See what I'm saying? So you could have just a whole lot of wasted
They
redundancy.
overlap between them.
Yeah, right. Whereas if one of them only got numbers, one of them only got nouns, one of them only got adjectives, you can imagine then they could specialize in the way we intuit, right? So I do think the routers learn to be smarter than just random, you know,
Hmm.
but they're not that smart, so it's unclear, I think. Clearly they work, but I think it's unclear. You shouldn't just assume that the routers are doing some like very, very intelligent mapping of which tokens go to which experts, you
Yeah.
know?
Yeah. Yeah. I mean,
Yeah.
there's simple mapping. What they learn is, I don't
Yeah.
know. I guess I think of the MLPs as kind of a vector database that you're going to have some vector in and you're going to have some vector that you look up on the output. And if you're doing kind of a similarity lookup, that the dumbest in the simplest case, the most naive case, brute force, you're going to dot product it with everything in the database, right? But there's smarter ways to do it where you can partition up that vector database and know what portion of the vector database to go look at. If you look at like a
Yeah.
CPU implementation of it, that's kind of what it does. It might do a couple little dot products here and say, okay, use that as an index. Is it above or below a threshold? Go use that as an index. This is the part of the database that it would be stored in. Um, and I've always felt like God, the GPUs have lots of compute available, but we're wasting it because we're doing this super naive vector database lookup. Whereas the MOE, it looks like it's getting a little closer to a smarter, more efficient lookup in that database. You're not vector.
I think it's a good intuition. Yeah, yeah.
Anyhow, sorry.
No, I mean, I think that's a good, solid, observation in that, the, the, or like the thought that I was having was that the, uh, was that for any given step, for any given prediction, kind of a toss up whether or not you are going to get whether you're going to get any mileage out of the the MOE architecture. But in aggregate, like if you're going to run this thing over, some number of sequences or batches, it's pretty safe to assume that you are going to like some of those predictions are going to be more efficient because of the expert routing versus the sparse or the fully dense approach.
More efficient, not necessarily more accurate, but yeah.
Yeah. Okay, let's see. We have twice as many active params, remarkably similar. Qwen3 model moved away from using a shared expert. Yeah, I thought that was kind of interesting as well. Moved away from using a shared expert. 2.5 of them, we did use a shared expert. But Qwen3 did not say why, which is unfortunate. Simply not necessary for training stability for their setup when they increased the experts from 2 to 8. And then they were able to save the extra compute cost by using only 8 instead of 8 plus 1. But then why is DeepSeek still keeping their shared? Is the question. Oh, updates. At that moment, we did not find significant enough improvement on shared expert, and we were worrying about the optimization for inference caused by a shared expert. No straight answer to this question, honestly. Fair enough.
You wonder how much
Yeah,
of that goes on
Right.
so
in these models.
if you think about it, right? If you had a hypothetical model with 200 experts or 201, and one of them was shared, okay, and you built a new model that was 210 experts, none shared, you could allocate those 9 additional experts just as replicas of what in the 201 expert model would have been a single shared expert. And now you can shard all of the traffic to the one shared expert 10 different ways across 10 different GPUs. So by not having a shared expert, you don't have a hotspot for traffic. And so it's possible that the Quen team was like, yeah, I mean, shared isn't so much better that if instead of sharing one, we just up the number of experts a little bit, now we can get much more balanced.
Ted, is the shared one? I guess I assume the shared one was copied on like every pipeline.
Um, that's not the naive implementation, but that it would be a clever way to reduce the hotspot.
Okay.
But so then you would have to add in some sort of round robin manager that's not part of the original computation graph to basically say, I have 10 replicas of my shared expert and let me round robin them.
Yeah.
I think, but you can see why, like, hypothetically, you could say, or I don't have to deal with that headache if I
Yeah.
just do 210 experts
Yeah. And it
and
does
say
make a
none are
difference.
shared.
Yeah. Can you remind me the relationship between Qwen3 and DeepSeek? Were they did they have a common root?
Not that I'm aware of. DeepSeek
Okay.
um, was a company that did crypto mining.
Yeah.
And then, of course, as Bitcoin gets less and less profitable as it gets through each tranche, right? Um, then eventually they moved to like hedge fund type predictions. Um, and I'm not aware of any connection between the founder there versus Alibaba does Quen, right?
Yeah, actually, I didn't mean the organizational relationship. I thought the models.
Oh,
I thought there
sorry.
was.
Yeah, their architectures are very similar right now.
Yeah, I thought they.
Slightly wider, slightly narrower here or there, but they've got very similar.
Okay, so
Um,
they've come up
they do
independently.
they do share a little bit of a hardware base in that these guys tend to have less powerful GPUs because of the US whatever embargo boycott thing. Whereas if you see a model trained by Anthropic or Meta, they tend to use the 8 by H100 nodes and
Yeah,
whatever,
yep.
tens of thousands, hundreds of thousands of those.
If you're flush with compute, why not use it, eh? Let's see. We've got small LM3, not nearly as popular as the rest of them, but an interesting model to include. Why is that, Sebastian? Good performance at small and convenient 3B size, right between 1.7 and 4B. Also shared a lot of the training details similar to Ulmo, which is rare and appreciated. True. Let's see. Okay, so there's performance to model size. Sure, Pareto frontier, if you will. We have, as shown in the architecture comparison below, architecture is standard. Sure. Use of NOPE, actually. I have not heard of this. No positional embeddings. Okay, let's see. We've got a vocab size, fairly similar. We have same SILU activations. We have feed forward. We have mask GQA. So QK RMS norm on the Quen 3. And then nope every fourth layer with GQA. Hidden, fairly similar. We have embedding DIM 2.5 and 2.04. And input tech, yeah, they look quite similar. Yeah, I'm curious about nope though. I'm not ringing a bell for me.
Nope.
Well, I mean, oh, there's a section on.
There we go. Perfect. Older idea that goes back to a 2023 paper, ancient. So throwback. Impact of positional encoding on length generalization in transformers. We'll save that one for later. Remove explicit positional information injection, like through classic absolute positional, or nowadays rope. Positional encoding is typically necessary because self-attention treats tokens independently of order. Absolute position solve by adding a embedding layer that's positional. Okay. Input embeddings after adding position information, which are fed to the LLM, are now different, despite original embeddings at the bottom all being the same. Okay, so token embeddings, assume all of these are the same, and then these are the values generally generated by an additional embedding layer. Sure. Checks out to me. Book plug by the book. Very good. Rope, on the other hand, solves this by rotating the query and key vectors relative to their token position. Okay, sure. In nope layers, however, no such positional signal is added at all. Not fixed, not learned, not relative, nothing. Very interesting. Even though there is no positional embedding, the model still knows which tokens come before, thanks to the causal attention mask. Do we have like something interesting about the masking here?
No, this is just the general way in
Okay, just
which
so that you just
you're never going to have a token attending to a word that comes later in the sentence.
sure. As a result, token at position T can only see at tokens at positions less than T, which just preserves the autoregressive ordering. Okay, so sure. There's still an implicit sense of direction baked into the structure. Can learn to exploit it if it finds it beneficial for the optimization objective. Sure. Not only
Yeah.
found
So
that no positional is necessary, has better length generalization. Interesting. Yeah, I would be quite curious what you guys have to say on that. There's a certain repo that's coming to mind.
if you remember the old bag of words, right?
Mhm.
The shark killed and ate the man killed and ate the shark, has the
Mhm.
exact same number of words. There, you just have the shark and man swapped. In
Mhm.
bag of words, those two are completely indistinguishable.
Hmm.
Okay, but in a transformer, even without the positional embeddings, when you see the shark, it can't see the rest of the sentence yet. And
Hmm.
so it may be able to infer and store some things in the token 2 residual stream that says, hey, I have a good guess that I'm the subject of this sentence.
Hmm.
Okay? And then when you see the word killed and ate, they may assume, they're not guaranteed to be right, but they may assume that the shark is the subject that did the killing and the eating. And then when you see the man, then the man is the object. Okay? So
Mhm.
these nope layers through that way, that's what Sebastian's talking about. Even though technically, by the time you get to the man and it's attending, if you were in layer one, okay, the very very first layer, the
Mhm.
reality is that layer cannot possibly
Yeah, yeah, yeah.
attend. It's going to get the same attention scores for the shark killed and ate the man and the man killed and ate the shark.
Right. But
Right.
the
Okay. But in
Mhm.
all the higher layers, this could actually look different because it's no longer just the shark. It could be the shark asterisk, I think I'm the subject, right? And blah, 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 blah. And so then when you're doing your attention, you can be attending to subject of the sentence, not just word.
Right.
Yeah. I'm like, my brain is like wanting to go down all the implications of that, but
So I
sure.
don't remember if it's that paper or a different rope paper, but they did a test where they trained like a small model, like a GPT-2.
Mhm.
Oh, there, they say the note paper.
Yeah,
They
yeah.
they they train the model not just with 1 out of 4, but with every layer using nope. Not a single freaking positional embedding anywhere. And the model was only like a few percent worse. I
Huh.
don't remember if it's perplexity or actual benchmarks like, MMLU, but the model, like, you would think that it would just be catastrophically bad, like Bag of Words. And somehow it learned to sort of, as it went, add information to the residual stream such that the higher layers basically had a sense for position, even though you did not manually provide any of it.
Oh,
It's pretty clever.
that's so
Yeah.
interesting.
Ted, do
Yeah.
you know, was there any discussion about, I would imagine that there's at certain levels, the order really doesn't matter. If I have a set of
Yeah.
10 independent concepts, it doesn't really matter what order they are.
Yeah, and when you start talking about the sentence 3 sentences ago or the sentence 10 sentences ago, how much difference does it really make, right?
Right, right. So I'm wondering if there's you get actually a benefit by not being distracted by the position in those cases.
Well, I have a bit of a contrarian opinion that I think that rope is actually messed up. When we've talked about rope before, I
Yeah,
really think that rope should be confined to a small subset of the data
yeah,
instead of running over the whole thing. And that when you want semantic information, you'll have unadulterated, unaltered semantic information. And when you want to know the really important things, the token immediately before me, 2 before me, 3 before me, maybe 4 or 5, but that's really about it. That's the most you're ever going to count.
yeah.
Um, and
Sure.
and so you could do a very tiny set of rope embeddings that just does 1, 2, 3, 4, 5 many.
Right, like sliding window rope kind of deal.
Yeah.
Yeah,
Yeah.
just something like that. Right, right. So yeah, so that's my like very contrarian, personal thing. But so like imagine you had biases in your model, and so at every token position you just simply add one with your bias, but you also grab anything that came before you. Then just through basically creating this running sum, you could get linear biases on your tokens,
Oh
where the first
yeah.
token has a one, the second token has a two, the third token has a three,
Right, right,
and
right.
so on and so forth. So you can imagine schemes where even without you constructing it, the layers could
Mhm.
devise a way to add their own positional embeddings, but
There
not
is
in
a
the very
model that
first
does that,
layer,
isn't there?
admittedly, not that one.
I thought there was a model that did that, that used a like a linear.
Well, there's alibi, but that's a separate thing,
Hmm.
right? But anyway, in the note paper, they showed that you don't have to give it anything, and it needs to know position. It does need to know position, but they're saying, but you don't have to architect it. You can just let the model figure out its own scheme for encoding position.
Well, yeah, and then like arguably, if you can learn it, you should, right? Because it's gonna necessarily have had to like traverse the all of the available n-dimensional space until it landed in something that could be like sufficiently useful as to get as to be like, okay, I this is my thing I know to get the test case, as opposed to
Right.
uh like injecting that externally by like deterministically, because it'll never be uniform in every generation, so you want it in the layers rather than hard coding it. It's
Yeah,
kind
that's
of
dead right. So in the Vaswani attention all you need paper, he had these sines and cosines that he manually created. And before rope came along, what people did was they did learned position instead of using the Vaswani ones, because exactly what you're saying. Just let the model figure it out.
yeah, yeah. Well, and so what? Yeah, so that probably works when you have dense models, because you're probably gonna need every layer to make sure that you get all of the bits that actually know where the next word is supposed to go, as opposed unless you have an MOE and you're sure that this MOE is the one that is tracking positionals, maybe, but that sounds really hard to arrange. Arguably, like not how MOUs work. Um, Although maybe the single expert there, if you were to try and do an MOE without any positional encoding, then that positional encoding has to be in the first expert, right? And but I guess you would, and then when it is mixed up, then whatever experts are currently activated other than the first one won't be able to hit the test set unless the test set is like grammatically indistinguishable, maybe. I don't know. That's a fun problem. I'm gonna have to chew on that for a while.
I'm not sure where you're going, but we,
Oh,
we are we are over time. But
Yeah, I was
but
just gonna
but I
say.
I, I feel like we would be remiss, because actually, Nope is one of the favorite names that I've seen in all of machine learning in like
absolutely.
my whole career, and so it I can't let us end without really just saying that when I first heard that term, I actually laughed out loud.
Absolutely. Yeah. I mean,
And kudos to these people for figuring out, you know, if rope is one thing and, whatever is another thing, like what do we call no positional embeddings? And it's just awesome.
nope. I love it. I love it. Yeah, absolutely.
All right. So is this our breaking point then?
Oh yeah. Time flies,
I
I
think it's a good one.
guess.
Yeah, and it's we got quite a bit still left, and apparently, two is next, right? Yeah, yeah. So we'll
Oh,
start there.
awesome. Yeah.
Start there
There's
next week.
a
And by the way, I don't know if has this document changed since we started, because it's now got the Quinn 3 next. I don't
He
remember.
he made some slight tweaks, but I think it's largely the same.
Was Quinn 3 in there?
yeah, let's see.
It says
Um,
on 11 September the team released, but the date at
It
the top of this thing says July 19th.
must be updated, yeah. because that was like 2 weeks ago.
Right.
So
Oh, sorry. Yeah. I think Qwen 3 Next was added. Sorry, I was thinking just Qwen 3, not Qwen 3 Next.
Oh, yeah.
Yeah.
Which is cool.
So
So
I
you're
think
keeping up to date.
yeah, we got a breakdown too.
And I wanted to hear about the Quint 3 next. So there you
Yeah.
go.
So maybe by the time we get to section 12, there'll be a 13, and by the time we get to 13, there'll be a 14. We can just keep going
Well, yeah,
forever.
no,
The great we go.
yeah, I hope that that's the case. I would love for this to be just like the place I can go back to if I ever need to know anything about like the temporal progression of LLM architecture improvement, and I can just go to this website. That sounds fantastic.
I think Ted stated it well. It's kind of nice to look at all the models and how they differ and how they're similar, rather than just one at a
really
time.
good.
I like this open discussion format too. It's pretty cool.
Yeah, absolutely.
All right, guys, I'm going to go ahead and stop the recording then.
That was good.